Welcome to a world where one of America's most cherished breakfast staples comes to life, where plump, sun-ripened grapes undergo a carefully controlled transformation from fresh fruit into the smooth, sweet spread that has graced tables for generations. This is the story of the modern grape jam factory, an industrial symphony where agricultural bounty meets food science precision, where tons of grapes flow through processing systems designed to capture the essence of the vineyard in shelf-stable jars that will travel thousands of miles and last months in pantries. What you're about to witness isn't simply cooking on an industrial scale. It's a sophisticated manufacturing process that balances tradition with technology, where the ancient art of fruit preservation through sugar concentration meets contemporary quality control systems, automated production lines, and rigorous food safety protocols. Grape jam represents more than a convenient spread. It's a product category with deep cultural roots in American food traditions, a staple that spans socioeconomic boundaries, appearing equally in school lunchboxes and upscale restaurant kitchens, in the iconic peanut butter and jelly sandwich, and in gourmet cheese accompaniments. The journey from vineyard to jar encompasses agricultural science, industrial engineering, food chemistry, microbiology, and supply chain logistics, all orchestrated to deliver consistent quality, food safety, and the nostalgic flavor that defines this beloved product. Our journey begins in the vineyards where jam-destined grapes grow under conditions quite different from their wine-producing cousins. While premium wine grapes are cultivated for complex flavor compounds, balanced acidity, and precise sugar levels measured as bricks, jam grapes are selected primarily for robust flavor, high natural sugar content, deep color extraction potential, and reliable productivity that makes commercial production economically viable. The Concord grape dominates American grape jam production, a cultivar developed in Concord, Massachusetts in the mid-19th century through the breeding work of Ephraim Wales Bull, who sought to create a grape that could withstand harsh New England winters while producing intensely flavored fruit. This variety produces characteristic dark purple berries with intensely fruity flavor and a distinctive foxy aroma, a term describing the unique, musky, perfumed quality that defines the taste profile consumers expect in grape jam and distinguishes it from European grape varieties. These grapes thrive in temperate climates with defined seasons, requiring cold winter dormancy where temperatures drop below 45 degrees Fahrenheit for extended periods to break bud properly in spring, followed by warm growing seasons that accumulate the sugars and develop the flavors that make exceptional jam. Vineyard layouts for jam grape production typically employ systems where vines are trained along wires suspended between posts, creating organized rows that facilitate mechanical operations while maximizing sunlight exposure and air circulation around the developing fruit clusters. The specific trellis design varies, with some vineyards using simple single-wire systems where vines are trained to a single horizontal wire at chest height, while others employ more complex multi-wire systems that support greater vine canopy development and potentially higher yields. The soil requirements for grape cultivation are less stringent than for many other fruit crops, with grapes tolerating a wide range of soil types from sandy loams to clay-based soils, though drainage is critical because waterlogged soils promote root diseases and reduce vine vigor. The vines themselves are perennial woody plants that can remain productive for decades, with commercial vineyards typically maintaining vines for 20 to 30 years before declining productivity justifies replanting. The planting density varies depending on trellis design, mechanization requirements, and regional practices, but typically ranges from 800 to 1,500 vines per acre, with row spacing determined by the width of mechanical equipment that will operate in the vineyard. The growing season follows a predictable progression beginning with bud break in spring, when warming temperatures and increasing day length trigger dormant buds to swell and produce new shoots. These shoots grow rapidly through late spring and early summer, developing leaves that power photosynthesis and flower clusters that will become grape bunches. Flowering occurs in late spring, typically in May or June, depending on latitude and local climate, with tiny, inconspicuous grape flowers self-pollinating to initiate berry development. The flowers are botanically classified as perfect, containing both male stamens and female pistils within the same structure, making cross-pollination unnecessary, though it may occur through wind or insect activity. Following successful pollination, the ovaries develop into berries that begin as small, hard, green structures containing high concentrations of organic acids, particularly malic and tartaric acids that give unripe grapes their intensely sour taste. The young berries remain small, hard, and intensely acidic through early summer in a phase called fruit set and development, but as midsummer arrives, a dramatic transformation called veraison begins. During veraison, which typically occurs in late July or August in northern hemisphere growing regions, the berries rapidly increase in size through cell expansion driven by water uptake and accumulation of sugars transported from leaves. The berries soften as cell walls undergo enzymatic modifications, and they develop their characteristic color, green varieties turning golden or amber, red and purple varieties developing their distinctive pigmentation through accumulation of anthocyanin compounds, the water-soluble pigments responsible for red, purple, and blue colors in many fruits and flowers. In Concord grapes destined for jam production, this color development is particularly important because the deep purple hue translates directly into the finished jam's appearance, with consumers expecting the characteristic dark color as a quality indicator. Simultaneously with these physical changes, the chemical composition shifts dramatically as acidity decreases through respiration and dilution, and sugar content increases through photosynthate translocation from leaves into the developing fruit. The sugars, primarily glucose and fructose in roughly equal proportions, accumulate to levels that will eventually reach 16 to 22% by weight, providing both the sweetness and the fermentable sugars that present preservation challenges requiring rapid processing. This accumulation of sugars continues through late summer into early fall, with growers monitoring Brix levels, the percentage of soluble solids, primarily sugars, as harvest approaches, because optimal harvest timing significantly impacts both yield and quality of the finished jam. Harvest timing for jam grapes targets peak sugar content and flavor development, while balancing practical considerations including weather forecasts, availability of harvesting equipment and labor, and processing facility capacity. Growers assess ripeness through multiple indicators, including Brix measurements taken with refractometers by crushing representative berry samples and measuring the refractive index of the juice, taste, taste evaluation of berry samples by experienced personnel who can detect the balance of sweetness and acidity, visual assessment of color uniformity across the vineyard, looking for blocks where all clusters have achieved full color development, and sometimes acidity testing through titration methods to ensure the sugar-acid balance meets specifications for jam production. The decision to commence harvest represents a critical juncture because grapes harvested too early will be insufficiently sweet and may lack full flavor development, requiring excessive sugar addition during jam production and potentially yielding inferior flavor profiles, while grapes left too long on vines risk over-ripeness that reduces acidity excessively, weather damage from rain or early frost, or losses to birds, insects, and diseases that attack ripe fruit. The mechanical harvesting that dominates commercial jam grape production employs impressive machines that straddle vineyard rows using vibrating mechanisms that shake grape clusters from vines while catching and collecting the fruit. These harvesters represent sophisticated engineering, typically costing hundreds of thousands of dollars, and incorporating hydraulic systems that control ground clearance and row alignment, shaking mechanisms powered by eccentric weights or hydraulic cylinders that create vigorous vibration at frequencies optimized to dislodge ripe grape clusters, while minimizing vine damage, catching systems using conveyor belts or panels that intercept falling grapes and transport them to collection bins, and cleaning systems that separate leaves, stems, and other vineyard debris from the grapes through fans that blow lightweight material away and screens or perforated surfaces that allow small debris to fall through while retaining grapes. The operation of these machines requires skilled operators who adjust shaking intensity, forward speed, and cleaning system settings based on vine condition, grape ripeness, and fruit detachment characteristics, because excessive agitation damages vines and may dislodge unripe fruit, while insufficient shaking leaves harvestable fruit on vines, reducing yield and economic return. The harvest proceeds at remarkable speeds, with modern machines capable of harvesting several tons per hour, allowing large vineyards spanning hundreds of acres to be picked at optimal ripeness rather than suffering quality loss from grapes remaining on vines beyond peak maturity while waiting for slower manual harvest methods. The harvested grapes accumulate in bins or bulk containers mounted on the harvester or in accompanying trucks, with typical bin capacities ranging from 1 to 4 tons. The filled bins are transported from vineyard to processing facility, and the urgency of this transport cannot be overstated because unlike wine grapes, where some producers deliberately delay processing for days or even weeks in techniques called extended maceration or carbonic maceration to extract additional flavor compounds, jam production benefits from rapid processing that captures fresh fruit characteristics while preventing fermentation that would begin within hours, as natural yeasts present on grape skins metabolize sugars into alcohol and carbon dioxide. The wild yeasts, primarily Saccharomyces and related genera that colonize grape surfaces from vineyard sources, remain dormant on intact berries, but become active when crushing ruptures skins and exposes sugar-rich juice, making the time between harvest and processing initiation a critical control point, affecting both yield and quality. Arrival at the jam factory marks the transition from agriculture to food manufacturing, where the grapes enter receiving systems designed for high-volume throughput while maintaining traceability and quality control. Trucks or trailers carrying grape loads back up to receiving stations, where various unloading methods are employed depending on facility design and grape condition. Some facilities use dump hoppers, where entire bins are mechanically tilted to discharge grapes onto conveyors, while others employ auger systems or hydraulic pumps that move grapes through enclosed pipework. The receiving systems are designed to handle the immense volumes that arrive during harvest season, potentially processing hundreds of tons daily during peak harvest periods. Initial inspection occurs at this receiving stage, with quality control personnel sampling incoming loads to verify sugar content through refractometer testing, assess overall fruit condition by examining berry integrity and looking for excessive mold or rot, evaluate color development to ensure fruit has reached adequate ripeness, and screen for excessive foreign material including leaves, stems, soil, or other contaminants that might have been collected during mechanical harvest. This receiving inspection provides critical quality control, establishing baseline fruit quality and enabling traceability if quality issues emerge later in production, with documentation systems recording load identification, source vineyard, harvest date, and quality parameters for each incoming delivery. The grapes flow from receiving through destemmers, machines that separate individual berries from the stems and rachis structures to which they're attached. Because while small amounts of stem material might be acceptable and even contribute some tannins and structure, excessive stems would contribute bitter, astringent flavors, introduce fibrous material that creates textural defects in finished jam, and interfere with processing equipment through wrapping around agitators or clogging pumps and heat exchangers. The destemmers work through several mechanical principles, with common designs employing rotating drums with perforations sized to pass individual berries while retaining larger stem structures, or crusher destemmers that use rotating paddles within perforated cylinders, where the paddles break apart clusters and separate berries from stems, while the perforated cylinder allows berries to pass through while retaining stems. The effectiveness of destemming is monitored through periodic sampling of the destemmed product, with quality targets typically specifying that stem material should represent less than 1 or 2% of the total weight. The cleaning phase employs water-based washing systems where grapes pass through tanks or channels, while water sprays and agitation remove field dust, pesticide residues if any remain from vineyard applications, surface microorganisms including the natural yeast populations that colonize grape skins, and any remaining stem fragments or foreign material that pass through destemmers. The washing water often contains food-grade sanitizers, such as chlorine at concentrations of 50 to 200 parts per million, or peroxyacetic acid, or ozone, at controlled concentrations that reduce microbial populations on grape surfaces without leaving harmful residues or adversely affecting grape flavor. The water temperature is controlled, typically maintained cool to avoid initiating fermentation or causing thermal damage to the fruit, with temperatures generally below 60 degrees Fahrenheit. Following washing, the grapes are drained and may pass through air knives, high-velocity air streams that blow surface water from the fruit, or vibrating screens that allow water to drain while transporting grapes forward. The washing water is typically recirculated through filtration and treatment systems that remove suspended solids and maintain sanitizer concentrations, with periodic discharge and replacement to prevent accumulation of dissolved sugars, organic matter, and contaminants. The clean grapes now advance to crushing equipment that ruptures the berry skins and releases the juice and pulp that will become jam. The crushing operation represents a critical processing step that determines much about the finished jam's textural and flavor characteristics. Crushers range from simple roller mills consisting of parallel rotating cylinders with adjustable gaps between them, where grapes are squeezed between the rollers, causing skin rupture and juice release, to more aggressive hammer mills, where rapidly rotating hammers impact and shatter the grapes, or positive displacement pumps that force grapes through restrictions, causing complete maceration into uniform slurry. The intensity of crushing affects the final jam characteristics in multiple ways. Gentle crushing that merely ruptures skins while leaving seeds and pulp relatively intact preserves more discrete fruit structure and can potentially yield jam with discernible fruit pieces and more complex texture, while aggressive crushing that completely homogenizes skins, pulp, and seeds creates smooth, uniform products, but may extract undesirable compounds from seeds, including oils and bitter phenolic compounds that create off flavors. Many manufacturers employ a combination approach where initial crushing is followed by screening operations that separate various fractions of the crushed grapes, allowing selective recombination to achieve desired texture and flavor profiles while removing components that would create quality issues. Screening equipment, typically rotating cylindrical screens or vibrating flat screens with precise mesh or perforation sizes, separates grape juice and fine pulp particles from skins and seeds based on particle size. The juice and pulp pass through the screen openings, while larger particles are retained, creating distinct streams that can be processed differently. Some formulations incorporate all fractions, simply ensuring uniform distribution, while others selectively remove seeds entirely or partially remove skins to create smoother textured products or reduce tannin content that can contribute astringency. The seeds, if removed, represent a potential byproduct stream, with some facilities extracting grapeseed oil, a premium cooking oil rich in polyunsaturated fatty acids and antioxidants, or processing seeds into animal feed supplements, transforming what would otherwise be waste into value-added products. The crushed grape material, now a mixture of juice, pulp, skins, and potentially seeds, depending on the formulation strategy, enters the cooking system where the transformation into jam occurs through carefully controlled heating that accomplishes multiple objectives simultaneously. Industrial jam cooking employs various equipment configurations depending on production scale and product specifications, with batch cooking in steam-jacketed kettles, representing the traditional approach still used by smaller operations and for premium products, while large-scale commercial production increasingly employs continuous cooking systems that process product in continuous flow rather than discrete batches. The batch kettle cooking system uses large hemispherical or cylindrical vessels, typically constructed from stainless steel and jacketed with a secondary wall through which high-pressure steam flows, transferring heat through the vessel wall into the grape mixture. These kettles range from a few hundred gallons to several thousand gallons capacity, with the size selected based on production volume requirements and product changeover considerations, because larger kettles offer economies of scale but reduce flexibility for producing multiple varieties or formulations. The cooking process serves multiple critical functions that transform grape juice and pulp into shelf-stable jam. First and foremost, cooking concentrates the mixture through water evaporation, raising the solids content from the 15 to 20% typical of grape juice to the 65 to 70% or higher required for jam consistency. Because jam is defined not just by its fruit content, but by its total soluble solids concentration that creates the characteristic thick, spreadable texture while providing preservation through reduced water activity. Second, cooking activates natural and added pectins that create the gel structure characteristic of jam, because pectins require heat to dissolve and hydrate before they can form the three-dimensional network that traps water and creates gel structure. Third, cooking sterilizes the product through heat, destroying spoilage organisms, including yeasts, molds, and bacteria that would cause fermentation or decomposition, and inactivating enzymes, including pectinases that would break down pectin and destroy gel structure, and polyphenol oxidases that would cause browning and flavor deterioration during storage. Fourth, cooking develops flavor through multiple chemical reactions, including Maillard reactions between amino acids and reducing sugars that create hundreds of flavor and aroma compounds, contributing complexity and depth. Caramelization of sugars that creates distinctive caramel notes and brown colors, and concentration effects that intensify the grape's natural flavor compounds. The cooking temperature is carefully controlled, typically maintained at temperatures between 220 and 228 degrees Fahrenheit, temperatures selected to achieve multiple objectives. They're sufficiently high to drive water evaporation at rates enabling reasonable cooking times. They achieve sterilization through thermal death of microorganisms and enzyme inactivation. They enable proper pectin activation and gel formation, but they're not so excessive as to cause extensive darkening through caramelization or development of strongly cooked flavors that would mask the fresh fruit character that consumers value in premium jams. The atmospheric pressure boiling point of pure water at sea level is 212 degrees Fahrenheit, but the dissolved sugars in grape mixture elevate the boiling point through the colligative property of boiling point elevation, where dissolved solutes raise the temperature required for vapor pressure to equal atmospheric pressure. This boiling point elevation increases progressively as concentration proceeds and sugar content rises, providing a convenient indicator of concentration progress that experienced jam makers have used for generations, knowing that jam has reached proper consistency when it boils at approximately 220 to 225 degrees Fahrenheit at sea level. The addition of ingredients occurs during cooking, with sugar being the primary additive in traditional jam formulations. Sugar serves multiple functions beyond simply providing sweetness. It acts as a preservative by reducing water activity to levels that inhibit microbial growth, with high sugar jams achieving water activity values below 0.85, where most spoilage organisms cannot multiply. It contributes to the gel structure by interacting with pectin molecules and acids to promote gel formation. It provides body and mouthfeel, creating the characteristic viscous, coating texture that distinguishes jam from syrup or juice. And it provides the characteristic glossy appearance that signals quality to consumers. The sugar quantity is substantial, with traditional recipes using roughly equal weights of fruit and sugar, yielding finished jam that's approximately 50 to 55% sugar by weight, though modern formulations may reduce sugar content to create reduced sugar products that appeal to health-conscious consumers concerned about excessive sugar consumption. Reducing sugar content presents technical challenges because the preservation and gelling effects of sugar must be compensated through alternative means, typically requiring higher pectin levels, sometimes utilizing specialized low-sugar pectins that gel at lower soluble solids concentrations, addition of calcium salts that promote pectin gelation through ionic cross-linking, and potentially incorporating preservatives such as potassium sorbate to inhibit mold growth that would occur at the higher water activity of reduced sugar products. Pectin, the gelling agent that gives jam its spreadable consistency rather than flowing like syrup or standing firm like gelatin, may be added if natural grape pectin levels are insufficient to achieve desired gel strength. Pectin is a complex polysaccharide found naturally in fruit cell walls, where it functions as a structural component cementing cells together, and its ability to form gels in the presence of sufficient sugar concentration and acidic pH creates jam's characteristic texture. The pectin content of grapes is relatively low compared to pectin-rich fruits like apples, citrus, or quinces, necessitating pectin addition in most commercial grape jam formulations. Commercial pectins are typically extracted from citrus peels or apple pomace through acidic extraction, followed by precipitation with alcohol and drying, and are available in various grades optimized for different applications. High methoxyl pectins, the traditional type, require high sugar concentrations, typically above 55%, and acidic pH between 3 and 3.5 to gel properly, making them ideal for traditional jam formulations. Low methoxyl pectins can gel at lower sugar concentrations and over broader pH ranges through calcium-mediated cross-linking, making them suitable for reduced sugar or no sugar added products. The pectin addition rate is carefully calculated based on the pectin grade, desired gel strength, and formulation characteristics, with typical rates ranging from 0.5 to 2% of the finished jam weight. Acid adjustment may occur through citric acid or lemon juice addition, because proper gel formation requires pH levels typically between 3 and 3.5. And if grapes are insufficiently acidic, either because the variety has naturally lower acidity or because the grapes were harvested at very high ripeness when acidity has decreased substantially, supplementation ensures proper pectin gelation and provides the tart flavor notes that balance sweetness and prevent cloying perception. The pH is monitored through regular testing using pH meters or pH papers, with adjustments made through careful citric acid addition, typically introduced as a solution rather than as dry powder to ensure even distribution. Beyond these primary ingredients, some formulations may incorporate additional components, including natural fruit flavors or essences, to enhance grape character that may be diminished during cooking. Antioxidants, such as ascorbic acid that prevent oxidative browning and preserve color and flavor during storage, or in some mass market products, artificial colors to intensify the purple hue that consumers expect, though premium products increasingly avoid artificial colors in response to consumer preferences for minimal ingredient lists. The cooking process requires continuous monitoring and adjustment, with operators or automated control systems tracking multiple parameters including temperature, measured through thermocouples or resistance temperature detectors positioned within the cooking vessel, solids concentration measured as bricks through online refractometers or determined through manual sampling and laboratory testing, viscosity that increases dramatically as concentration proceeds and can be monitored through empirical methods like observing how the mixture flows from a spoon or through sophisticated rheological instruments, and pH to ensure acidic conditions remain within target ranges. The physical changes during cooking are dramatic. What begins as a relatively thin, watery mixture of grape juice and pulp gradually thickens as water evaporates, the boiling becoming more vigorous and creating characteristic, large, slow bubbles, rather than the rapid, small bubbles of boiling water, the color deepening and intensifying as concentration increases and some caramelization occurs, and the aroma evolving from fresh fruity notes to more complex cooked fruit and caramel characters. The agitation during cooking is critical to prevent scorching, the localized burning that occurs when grape solids settle onto the heated kettle bottom, where they're exposed to the highest temperatures and can char, creating burned flavors that contaminate the entire batch. Agitation systems in batch kettles typically employ anchor or paddle-style agitators driven by electric motors with speed controls, rotating continuously throughout the cooking process at speeds sufficient to keep solids suspended and prevent settling while avoiding excessive agitation that would incorporate air bubbles, creating foam. Foam formation represents an operational challenge because foam insulates the product surface, reducing evaporation efficiency, and can boil over vessel walls, creating production losses and safety hazards. Foam control is achieved through proper agitation speed selection, addition of small quantities of food-grade anti-foaming agents typically based on silicone compounds or fatty acids, or mechanical foam breakers that physically disrupt foam bubbles. As the jam approaches proper consistency, determined through the temperature, bricks, and visual indicators discussed earlier, the heating is reduced or terminated, and the jam is prepared for filling. In batch operations, this means the steam to the kettle jacket is shut off and the jam is allowed to cool slightly, typically to temperatures around 195 to 205 degrees Fahrenheit, hot enough to maintain fluidity for pumping and filling, while cool enough to reduce the risk of jar breakage from thermal shock when hot jam contacts glass containers. In continuous cooking systems, the concentrated jam flows continuously from the heating section through holding tubes that provide residence time for complete sterilization, then to the filling stations. The filling operation represents a critical control point where hot jam must be transferred into containers under conditions that maintain sterility achieved during cooking and prevent recontamination that would compromise product safety and shelf life. The jam, at temperatures exceeding 190 degrees Fahrenheit as it reaches filling stations, flows through heated pipework systems typically constructed from stainless steel with steam jackets or electric heat tracing that maintains temperature and prevents cooling that would increase viscosity and create pumping and filling difficulties. The flow is typically driven by positive displacement pumps capable of handling viscous, particulate containing fluids, with pump types including lobe pumps with two rotating lobes that create cavities that capture and move product, or piston fillers, where reciprocating pistons draw product into cylinders and then discharge it into containers. The jars that will receive the jam have been previously prepared through washing and often thermal sterilization to eliminate any microorganisms present from manufacturing, storage, or handling. Glass jars, the dominant packaging format for retail jam, are manufactured through high-temperature glass forming processes that produce sterile containers, but during transportation, warehousing, and handling before filling, they may accumulate dust and potentially microbial contamination. Jar preparation systems typically include inverting and rinsing equipment, where jars are turned upside down and rinsed with hot water or steam, followed by draining and sometimes brief heating to sterilization temperatures. The prepared jars advance on conveyors to filling stations where they're precisely positioned under filling nozzles. The filling equipment, typically volumetric or piston fillers as described earlier, dispenses precise quantities of jam into each jar. The fill volume is controlled to deliver the declared net weight printed on the label, typically verified through statistical sampling and weighing, while leaving appropriate headspace, the gap between the jam surface and the underside of the jar lid, that accommodates thermal contraction during cooling while providing proper vacuum seal formation. The headspace is typically 1/8 to 1/4 inch, sufficient to allow the required vacuum to develop, but not so excessive as to allow excessive oxygen above the product that could promote oxidative deterioration. The filling speed is impressive in modern facilities, with production lines capable of filling hundreds of jars per minute through multiple filling heads working in parallel, each head servicing a lane of jars advancing on parallel conveyor tracks. Immediately following filling, while the jam is still hot, lids are applied and sealed onto the jars through capping equipment that places closures onto jar finishes, the threaded or otherwise shaped jar opening, and applies the torque or force necessary to engage threads and compress gaskets, creating seals. The most common closure system for jam employs twist-off metal lids, typically manufactured from tin plate steel with internal coatings that prevent corrosion and provide food contact compliance, with compound sealants, plastisol or similar materials, applied to the lid's underside that flow and conform to the jar finish under compression, creating hermetic seals as the product cools. The capping machines employ multiple spindles or heads that simultaneously cap multiple jars, with torque-controlled drive systems ensuring consistent cap application that's tight enough to create proper seals but not so tight as to damage threads or make consumer opening difficult. The hot filling process, called hot fill or hot pack, exploits the jam's elevated temperature to create vacuum seals as product cools. As the hot jam sealed within the jar cools over the hours following filling, it contracts, both the jam itself, shrinking slightly in volume through thermal contraction, and more significantly, the headspace air cooling and contracting according to gas laws. This contraction creates negative pressure or partial vacuum within the sealed jar, typically achieving vacuum levels of 10 to 15 inches of mercury below atmospheric pressure, and this vacuum pulls the center of the metal lid downward, creating the characteristic concave appearance and the audible pop when consumers open jars, breaking the vacuum seal. This vacuum seal serves multiple preservation functions. It prevents oxygen from entering the jar during storage, limiting oxidative degradation of colors, flavors, and nutrients. It creates an anaerobic environment hostile to aerobic spoilage organisms. And it provides a tamper evidence feature because lid button position indicates whether the seal has been compromised. Some facilities employ additional processing steps, including pasteurization tunnels, where filled, sealed jars pass through temperature-controlled zones, ensuring adequate heat treatment, though the hot fill process itself often provides sufficient lethality for high sugar jam formulations where the combination of low pH, high sugar content, and thermal processing creates multiple preservation hurdles that make the product shelf-stable. The pasteurization tunnel, if used, typically consists of several zones where jars are sprayed with water of progressively changing temperatures, beginning with relatively hot water to avoid thermal shock, maintaining at pasteurization temperature, typically 185 to 200 degrees Fahrenheit, for a defined residence time calculated to achieve required microbial reductions, then cooling through zones with progressively cooler water to bring jars to temperatures suitable for further handling. The sealed jars advance through cooling zones where temperature is gradually reduced to levels suitable for labeling and packaging. Rapid initial cooling is desirable to minimize the time spent at temperatures between 120 and 140 degrees Fahrenheit, where thermophilic spoilage organisms, heat-loving bacteria that survive pasteurization temperatures, could potentially germinate and multiply. Though, in practice, the low water activity and low pH of properly formulated jam make this risk minimal. The cooling is typically accomplished through multi-zone conveyor systems, where jars pass under sprays or through tunnels with controlled air or water cooling, with gradual temperature reduction, preventing thermal shock that could crack glass. The cooling process may extend 30 to 60 minutes, by which time jars have reached temperatures of 80 to 100 degrees Fahrenheit, suitable for subsequent handling. As jars cool and vacuum seals form, quality checks verify seal integrity through various methods, including visual inspection, where trained personnel examine the lid button position, automated vacuum detection systems that use sensors to verify the concave lid deflection indicating proper vacuum, or sampling and destructive testing, where random jars are selected and vacuum levels measured with gauges after puncturing lids. Improperly sealed jars are rejected and either reprocessed if the failure is detected immediately or discarded if discovered later after sufficient cooling that reprocessing would require the entire heating and filling cycle repeated. The labeling equipment, positioned after cooling and seal verification, applies printed labels or pressure-sensitive labels to the cooled jars, providing product identification through brand names and graphics, ingredient declarations listing all components in descending order by weight as required by regulations, nutritional information formatted according to regulatory standards, manufacturing codes enabling traceability, and best by dates indicating the period during which optimum quality is expected, though jam typically remains safe well beyond these dates given its shelf-stable formulation. The labeled jars are grouped into retail packaging configurations, with formats varying based on market channel and customer requirements. Some retail channels receive individual jars, particularly in food service or bulk retail, where individual units are sold, while others require multi-packs, where several jars are grouped together, often shrink-wrapped with printed film that provides additional product information and graphics, or loaded into corrugated cartons printed with product identification and handling instructions. The grouping and packaging operations employ a combination of automated and manual labor, with jars advancing on conveyors through shrink-wrap tunnels where they're enveloped in plastic film and pass through heated tunnels that shrink the film tightly around the jar group, or diverted to packing stations where workers manually load jars into cartons that are then sealed with tape or glue. The packaged jam accumulates on pallets in the warehouse staging area, with pallet loads typically containing thousands of jars arranged in stable stacking patterns optimized for cube utilization, the efficiency of filling available space, and physical stability during transportation and warehousing. Standard pallet dimensions in North America are 40 inches by 48 inches, though other sizes exist in international markets, and loads are stacked to heights determined by product weight, packaging strength, and warehouse or transportation equipment limitations, typically ranging from 4 to 6 feet. The pallet loads are secured with stretch wrap, a highly stretchable plastic film applied while under tension that wraps around the load, creating compression that holds packages in place, supplemented sometimes with corner boards or top caps that distribute compression forces and protect upper layers from damage. These completed pallet loads represent the culmination of the vineyard to jar journey, shelf-stable products that will maintain quality for months or even years when stored under appropriate conditions, typically cool, dry environments away from direct sunlight that could cause color fading and accelerate quality degradation through light-catalyzed oxidation reactions. The distribution network moves these pallets from factory warehouses through regional distribution centers operated by manufacturers, food distributors, or large retail chains, with inventory management systems tracking product location, age, and movement velocity to optimize first in, first out rotation, ensuring oldest product moves to market first, while freshest remains in inventory. Transportation from factory to distribution centers typically occurs in dry van trailers, since jam doesn't require refrigeration, with full truckload quantities for major customers or less than truckload consolidation for smaller customers or diverse orders combining multiple products. The distribution centers serve as consolidation and cross-docking points where incoming full pallet loads are broken down into mixed pallets or smaller quantities matching retail store orders, with picking operations selecting specific SKUs, stock keeping units differentiated by size, flavor, or package configuration, and assembling them into store-specific loads. The final transportation mile from distribution center to retail store occurs in delivery trucks, making regular routes, often 2 to 3 times weekly to high-volume stores, with jam competing for truck space and delivery priority against the entire grocery assortment. Upon arrival at retail, the jam is received at store backroom docks, checked against orders and invoices, and moved to storage or directly to the sales floor. Store personnel place jars onto shelves in the jam and jelly aisle, one of the most stable and predictable categories in the grocery store, with dedicated linear footage allocated based on sales velocity and profit margins. The merchandising arranges products to maximize visibility and accessibility, with premium brands often at eye level, while value brands and store brands occupy upper or lower shelves, and with flavors organized to help consumers navigate choices. The consumer purchase decision for grape jam is influenced by multiple factors, including brand loyalty built through years of repeat purchase, price sensitivity with promotions and discounts driving significant purchase shifts, package size selection based on household consumption patterns, and increasingly formulation preferences as consumers choose between traditional full sugar products and reduced sugar alternatives, organic certified products versus conventional, and single variety grape jams versus blended fruit options. The jam category is mature and highly competitive, with established national brands competing against aggressive private label programs that often match quality at lower prices, creating constant pressure on manufacturers to differentiate through innovation, quality improvements, or marketing effectiveness. The final experience of consuming grape jam provides the ultimate validation of the entire journey from vineyard through factory to table. The consumer opens the jar, breaking the vacuum seal with the characteristic pop, and immediately encounters the aroma, intensely fruity with the distinctive Concord grape character that defines American grape jam. The color, deep purple verging on burgundy, visually communicates richness and intensity. The texture, when spread on toast or bread, should exhibit the characteristic jam consistency, thick enough to maintain position without flowing off the bread, but soft and spreadable without requiring excessive force that would tear delicate bread surfaces. The flavor delivers concentrated grape sweetness balanced by subtle acidity, with the complex flavor notes developed during cooking complementing the fruit's natural character. The mouthfeel should be smooth without excessive seediness or gritty texture from sugar crystallization, with appropriate cohesiveness that allows clean spreading. Beyond simple consumption as a spread, grape jam serves multiple culinary functions as an ingredient in baking, where it fills pastries, thumbprint cookies, and layer cakes, as a glaze for meats, where its sweetness and acidity complement savory proteins, or as a component in sauces and marinades. These diverse applications demonstrate how a product designed originally for preservation has evolved into a versatile culinary ingredient valued for the convenience of shelf-stable fruit flavor available year-round, regardless of season. The grape jam industry continues to evolve, responding to changing consumer preferences, competitive pressures, and operational challenges. Health and wellness trends drive development of reduced sugar and no sugar added formulations, organic and natural products free from artificial ingredients or preservatives, and even innovations like protein fortified jams that position the product as more nutritionally valuable.